Okay, so I'm going to discuss the issue of emergence of space and time in quantum gravity. Of course, I will focus on particular brand of quantum gravity. And before getting there, in a sense, I will just repeat the encouragement of Chris and Nick, two philosophers, to join us, quantum gravity theorists. The main motivation is the one written there. I don't think I'm being particularly subtle in phrasing it. It's just that quantum gravity is very hard both conceptually and mathematically, plus all the experimental difficulties. So on the conceptual part in particular, philosophers have a lot to help. So, and there are two main difficulties that I would say are the main difficulties of quantum gravity. One is to identify what the fundamental degrees of freedom of space-time are and their quantum dynamics. And the second is to show how general relativity is obtained at the effective classical level. The point is that the additional difficulty comes when the fundamental degrees of freedom that different quantum gravity approaches suggest are not spatio-temporal themselves. So that is, they're not associated to any smooth space-time manifold, which is what we usually understand for spatio-temporal. So the additional problem that arises is how are a space-time that is a smooth manifold in its geometry obtained from the fundamental degrees of freedom which are not spatio-temporal. And let me just point out that this is already much beyond the already difficult issue of the quantum to classical transition in the standard quantization of GR, for example in quantum geometrodynamics. So I'll give you some example of this. There's been lots of progress in several approaches. So I will discuss these two issues, what are the candidates for the fundamental degrees of freedom in some of them, and then I will discuss the problem of the continuum, which to date is the one that really remains open, even when you have identified candidate fundamental degrees of freedom. And because this is going to be a conceptual tour de force, then here is where philosophy can and should help. So I encourage the philosophers to join us in the mud being the ones of untested theories, shaky theoretical grounds and mathematical grounds, new mathematics to be learned, and so on. So the plan of the talk is the following. So because I want to discuss the emergence of space-time, I have to first convince you that space-time disappears in quantum gravity at some level. And then I will move on to give a very brief survey of what some quantum gravity approaches suggest as the pre-geometric structures that are more fundamental than space and time. I will say something about the second quantization of quantum gravity, that is the group field theory framework. And then I will try to discuss a little bit more the conceptual aspects of the notion of emergence. So what does that mean? And in particular, in the case of space-time, what can it mean for space and time to emerge? I will give a non-quantum gravity example of emergence to clarify at least this aspect of the story. And then I will show one concrete example of emergence of space and time in quantum gravity, in particular in the group field theory approach. And then we'll comment on the general problem of emergence of space-time in light of the particular example I will have given. So I will be brief on this very first slide. There are several hints in coming from classical, semi-classical, and quantum GR that space and time disappear at the fundamental level. Already in semi-classical GR, the very notion of locality is challenged in many ways. There are minimal length scenarios, there are non-commutative space-times, and locality is one of the defining features of what we mean by space-time. There is the issue of space-time singularities in GR that could be interpreted minimalistically as showing that we need quantum corrections to classical GR, but one can interpret it in a more radical way as showing the breakdown of the continuum description of space-time itself. There is all the body of work on black hole thermodynamics. First of all, people have suggested that the solution of the information loss paradox in black holes requires a fundamental non-locality in the description of space-time. because black holes are nothing else than particular regions of space-time. But there is a more general statement that if space-time itself, in particular black holes, have an entropy, then it has a microstructure. If it has a microstructure, the standard description as a smooth manifold has to break down. In particular, because the entropy seems to be finite. And this is taken to imply a discrete fundamental structure. I mentioned very briefly also the derivation by Jacobson and collaborators of the Einstein's equation as an equation of state, which basically says that if you have only reproduced the kinematics of general relativity, that is metric and matter fields, then the GR equations, the dynamics of space-time, come just from thermodynamic considerations. And this is another way to suggest that maybe the usual description is not fundamental at all. And last, I mentioned several insights from analog gravity models in condensed matter physics, which show that an effective curved geometry and matter fields may come from non-geometric atomic theories. At this level is an analogy, but it's going to be a little bit more than that in the following. Okay, so let me just briefly mention some of the candidate fundamental degrees of freedom, fundamental substructures of space-time suggested by various approaches. The main one that I will focus on is loop quantum gravity, and I will summarize loop quantum gravity in 2 slides, so obviously I'm leaving aside quite a bit of stuff. It started as a canonical quantization of continuum GR, but the end point is much more radical. You end up with a Hilbert space of the theory, which decomposes into graph-based sectors. That is, that to any graph, that depending on the version of the theory, you can understand it as embedded or not in some continuum manifold. For every graph you can think of, there is an associated Hilbert space with functions defined just on the basis of algebraic data, group elements or spins of group representations. In particular, a generic state is a superposition of spin networks, that is, states associated to graphs labeled by SU2 representations, purely algebraic data. And a generic state is an arbitrary superposition of such graph-based states. So the technicalities are not important. What I only want to say is that instead of having a space-time with a metric on it, what you're left with after part of the quantization is graphs and algebraic data. So you are very much beyond the standard geometric picture. You can try to define the theory canonically by imposing the analog of some Hamiltonian constraint equation on generic states and look for solutions of that equation. Or covariantly, the pre-geometric nature of the theory becomes even more evident because a generic history, a generic evolution of a spin network will involve a change both in the combinatorics of the graphs and in the algebraic data. So a particular process of evolution of spin networks, you can say an interaction for these discrete building blocks, is going to be labeled by two-dimensional combinatorial objects, a two-complex, labeled by the same type of algebraic data. So not only space, but also space-time is replaced by combinatorial and algebraic structure. And then you can define a purely algebraic and combinatorial counterpart of a path integral that goes under the name of spin-fold model. From another corner, another way to obtain candidate substructures for space-time which are not geometric in the usual sense is simplicial quantum gravity. There you try to define a covariant sum over histories, again the analog of a gravitational path integral, but here the discrete counterpart of a continuum space-time is a triangulation, that is a simplicial complex. And the discrete counterpart of the metric is taken, depending on the specific approach you work with, either by edge lengths, so just labels that associate to the edges of the simplicial complex, or by this very combinatorics of the triangulation in the dynamical triangulations approach. So in both cases, you have a pre-geometric substitute for what space-time really is. Let me now say a couple of words on the specific approach I will work with in the following, that is group field theory. It can be seen as coming from a variety of points of view, from matrix models through tensor models, and that will make it directly related to dynamical triangulations. Or, which is the way I'm presenting it here, is just an outcome of the loop quantum gravity program. In particular, in a way that I will try to clarify a bit, is just a second quantization of the same theory. In particular, you can see it is as the background independent quantum field theory a la Rovelli that the previous speaker was suggesting as the outcome of the program. So, in the next slide I'll tell you the relation with spin networks and loop quantum gravity. Here just give you the basic structures. The theory is defined as a quantum field theory for a complex field over a particular group manifold. Take a group manifold G and take 4 copies of that. So these are points on the 4 copies of the group manifold. These are the arguments of the field. Or you can work with the corresponding Lie algebra using a kind of Fourier transform. So it's a bit like a configuration and momentum space. The way you understand it, the way model building in this class of models go on, is that you start from the group manifold being the local gauge group of gravities. So in the Riemannian signature, the 4-dimensional rotation group, and in the Lorentzian signature, the Minkowskian signature, is the local Lorentz group of gravity, SO31. So you take 4 copies of them, and then you impose appropriate conditions. How you do it defines the specific model you work on, but they are such that you can put first a combinatorial tetrahedron in correspondence with the field. Like the basic quantum of the field is like a tetrahedron with 4 faces labeled by the 4 group elements or the 4 Lie algebra elements. And then you impose conditions that are meant to impose the geometricity of this tetrahedron. Meaning, after you impose appropriate conditions, the basic quantum of the field can be understood as a geometric tetrahedron for which you can talk of edge lengths, areas of triangles, and volume of the tetrahedron itself. We're talking about discrete geometry here, so we are still very far from any continuum geometry. I don't know what the first. The theory is motivated by a particular formulation of continuum gravity in terms of a topological BF theory plus constraints for people who know about it. So that's the basic, the initial idea. So you have a field whose quanta are this geometric tetrahedron. The sense in which is a second quantized version of loop quantum gravity, in this particular formulation adapted to a simplicial context, is the following: that you obtain the group field theory, specific group field theory models by applying standard second quantized reformulations of the loop quantum gravity Hilbert space with a given choice of the dynamics, of the quantum dynamics. You just rewrite it as a field theory, reinterpreting spin network states as many particle states, with each particle being a spin network vertex. This works, many works. A picture is clear. This is a spin network, a trivalent spin network with nodes with 3 links each coming out and fully connected. You just reinterpret it as 4 spin network vertices that you have chosen to be connected, but in general the corresponding state will be a many particle state made of 4 big quanta. The 4 vertices correspond to the spin network. So you do this, and then you build up the old field theory framework, in particular the fog space. The fog vacuum is the emptiest state, the no space state. There is nothing. You have not created anything. No topological nor geometric structure. The single field quantum is a spin network vertex, as I said, that you can put in correspondence with the tetrahedron by just topological duality. So there is one vertex for each tetrahedron. There are 4 links for the 4 faces of the tetrahedron. And a generic quantum state is going to be do want the updates. A generic quantum state is going to be an arbitrary collection of such spin network vertices, including the case in which you glued all the vertices across links. Or a collection of tetrahedra, including the case in which you glued the tetrahedra along common triangles. Okay? Then you define a classical action for the field theory with a kinetic that is a quadratic term and some higher order interaction term. And this class of models is peculiar as field theories because there is a combinatorial non-locality in the way you pair the arguments of the fields. I give you one example. Interpreting each field, as I did, as a tetrahedron, you can choose the combinatorics of the interaction term to match the gluing of 5 tetrahedra across common triangles to form a 4-simplex. Okay, so these are the 5 fields, each with 4 arguments, so 5 tetrahedra with 4 triangles each, and you identify arguments in the interaction, not in a strictly local way, by identifying all the arguments of all the fields at the same point, but pairwise to represent the gluing of tetrahedra across common triangles to form a 4-simplex. Take-home message. These are peculiar field theories because the way you glue together, you identify arguments as this peculiar non-locality. All the rest can be discussed at a more technical level, maybe after the talk. And then the quantum theory is defined by quantum field theory, that in particular you can expand in Feynman diagrams around the Fock vacuum, and by construction the Feynman diagrams are going to be dual to simplicial complexes of arbitrary topology. That is, they correspond to all the possible ways in which you glue 4 simplices across common tetrahedra. Okay, each interaction is a 4-simplex. Propagator glues 2 4-simplices across the tetrahedron. A generic Feynman diagram is an arbitrary gluing of such 4 simplices. And what happens is that the Feynman amplitudes are exactly spinfold models, so covariant versions of the dynamics of loop quantum gravity, so some of the histories for spin networks, or equivalently, simplicial gravity path integrals. So the point here is only that you're bringing together insights and mathematical structures from loop quantum gravity and simplicial quantum gravity. That's the only message of this part. Plus, repeating once more that you're obviously quite far from a description of space-time in terms of smooth manifolds. You have combinatorial and algebraic structures which are arbitrarily superposed, both at the kinematical level and at the dynamical level. That's why there is an issue with the emergence of space-time. So, because you do not have spatial-temporal or geometric structures in the definition of the theory, although you may carry sort of seeds of future geometry in space-time, you have to explain how continuum space-time and geometry emerge, which is where the context in which we're used to do physics. Okay, so before I show you an example of that, let me discuss the issue of emergence in the space-time context. So there is first of all a general issue with the notion of emergence. First of all, you can ask whether the theoretical description of some emergent property of your system of study can be reduced or deduced from the theoretical description of properties of the constituents of the same system. The answer is yes, then it's not clear in what sense you're talking about emergence at all, of something from something else. But if yes, then you may be tempted to say that then only the properties of the constituents are real, the real fundamental thing, and there's no real existence for the emergent property because you can reduce it to something more fundamental. Here I side with Jeremy and collaborators in stressing that in defining emergence as the appearance of properties that, although they may be reduced or deduced from fundamental from properties of fundamental constituents are novel with respect to the description of those constituents and robust, therefore reproducible. Also, I side with those people in stressing that the emergent, really to meaningfully speak of the emergence of a property requires some limiting procedure in the description of the system. This has been stressed also by Butterman, if it is the right way to pronounce the name. At the same time, although you need a limiting procedure, it's crucial that emergence in physical terms takes place before you take the full limit. So it requires approximations. The existence of a limit is required to define it, but physically you should expect it to take place before. The limit itself may be actually unphysical. Think of the thermodynamic limit in a condensed matter system. Infinite volume. Well, I mean, the system lives in the lab, so physically it's not that you expect it to happen in infinite volume. So, more particularly about space and time, there are additional issues when you start thinking about the possibility of emergence of space and time. First of all, it's much more difficult to just make a bit clearer what you mean by emergence. And here I will just define it. I will say that the problem of showing emergence of space and time is the problem of defining an appropriate approximation or limiting procedure that leads from the non-spatio-temporal fundamental quantum gravity degrees of freedom, for example spin networks or the like, to a continuum space-time and geometry. So it's a very sort of general, minimal definition of what I mean by emergence. But notice that it involves two a priori different limits, continuum and classical. And it's not obvious in which order you should take them. I cannot discuss the exact nature of the degrees of freedom, the procedure, the limits in general. You have to work with specific examples. So I will present one in the following. The more general challenge put forward by modeling is that of empirical incoherence. To really put it in a simple, maybe naive form, you may argue that local, that is spatio-temporal behaviors, are necessary for having empirical content at all. That is, if you do not have a theory with local behaviors, like any fundamental theory with no space and time concepts would be, would that be physically salient? Here I sided with the organizers, and not just because they allowed me to give a talk. Although that as a part. But beside that, the argument is quite convincing that local behaviors can be thought as just approximate concepts. And so the real issue is not just to show that you have or not local behaviors, but it's what it means to be physically salient. And again, you have to discuss it in example. So I'll do it in the following, to show you two examples of emergence in the quantum gravity and outside the quantum gravity context that are relevant for the issue. But let me just say here that it seems to me that this is a very common issue in physics. If we do not have direct access to fundamental constituents of a system, you may ask the same question. Is your theory of the fundamental constituents physically salient if there's no way you can access them? And the answer usually in physics is, well, it is if you can at least deduce testable consequences of their existence, of the existence of the fundamental degrees of freedom, even if you don't access them directly. Okay, let me give you one example that will be the prototype for the quantum gravity example I will show. And I'm not keeping track of time. I don't know if I should speak much faster or much slower.
There's about 25 minutes left in the session as a whole.
In the session as a whole?
Including questions, yeah.
That is my talk plus questions.
Yeah, how long are we giving for questions?
Okay, fine.
Like 15?
Anyway, so 15 minutes should be enough.
Yeah, okay.
I'm okay. In case you tell me.
Yeah.
30 plus 15 was
So,
you can give it flexible.
okay, so the example I want to discuss briefly as a template for the quantum gravity example is that of Bose condensates. I hope that by clarifying the issues in this context, the general conceptual setup will not be murky anymore, because we all agree that those condensates exist, that they satisfy the properties that I will mention. So there we know what the fundamental theory of everything is. Is the quantum field theory for the bosonic atoms. And you forget about the electromagnetic field, you mimic it by the interaction between atoms, so you mimic it by some potential U there. Okay? So it's a non-relativistic field theory, but you don't need relativistic properties for what I'm going to say. The generic microscopic state will involve a finite number of atoms, usually. Discrete quantum numbers if you put the system in a box, as usually you have your quantum condensate in a box, it is in some trap or in a container in your lab. So the momenta of the atoms are quantized. And as such, if you just take a finite number of atoms, there's no special collective property. In fact, you describe the physics by studying the atomic collisions and so on. However, something happens when you take the continuum limit. That is, you go to large volume and large numbers, possibly infinite number of atoms in your description. What exactly happens depends on macroscopic parameters. In fact, the system organizes itself in different phases. One of them is the condensate. So at very low temperature, constant pressure, weak interactions and so on, the system condenses. That means that there is a new relevant, still approximate of course, vacuum that you use as your trial state to describe the system, which is a condensate state in which all the particles, all the atoms have the same state, have the same wave function. That's the simplest, I think, Hartree-Fock approximation or Gross-Pitayevsky approximation. I always forget the nomenclature. It involves a possibly infinite number of atoms, but still is described by a single collective wave function, which describes the condensate as a whole, the whole fluid, the whole system. Oops. Here, to come back to the previous discussion, the thermodynamic limit is crucial in order to think of condensation as a phase transition, as something that happens. There's no phase transition with 15 atoms or even 100 atoms if you don't take the thermodynamic limit. And crucial as well are all the approximations. The choice of this condensate vacuum is an approximation to what the real vacuum of the system is. But still, you can extract an effective dynamics for the whole fluid, for the whole condensate, by plugging this condensate ansatz into the microscopic dynamics, say the Schwinger-Dyson equation of the non-relativistic field theory, or the Schrödinger equation for the atoms. And you extract an equation which is the Gross-Pitayevsky hydrodynamics for the whole fluid. It's an equation for the collective variable that describes the whole fluid, the wave function that I was mentioning in the previous slide. If you want, you can rewrite it in explicit hydrodynamic flavor by splitting the wave function into the density and the velocity of the fluid. It's just cosmetics. So, in what sense you have emergence here? I hope we agree. There is first of all a new entity, the condensate fluid, in place of the atoms. You change the type of description. There's no point in discussing the fact that there are atoms there if you are at this level of description and if the system is in the condensed phase. This is not practical reason to do that. If you feel more comfortable with thinking that no, really there are atoms there and that's all I'm talking about, good, but it's more psychological than practical. There are striking, emergent new properties, and I don't have to stress the importance of superfluidity as a novel property in this phase for this system that you will not be able to see if you just look at the atoms. And it's a macroscopic property, it's not a property of the atoms. And this emergent behavior is robust. In fact, it is due to collective symmetries, it's due to the separation of scales and so on. Still, it doesn't mean that the microscopic theory is irrelevant, not at all. In fact, it enters directly the macroscopic one in the parameters, in the type of variables and so on. And again, the fact that there is emergence doesn't mean that there is no path from the microscopic physics to the macroscopic one. Actually, you can follow the path and derive the Gross-Pitescu equation analytically, quite nicely. And there is a big distinction even here between a continuum and a classical limit. The continuum features are due to the quantum features of the underlying system. If you were to take the classical limit before taking the continuum limit, you would just never reproduce the properties of the condensate. For example, superfluidity. So, in this case, I ask the question, is the microscopic theory physically salient, even if there's no way you could see the atoms, as it was thought a century ago? A bit more. I'm not an historian, so I'm allowed a little bit of approximation. Anyway, so what about quantum gravity? Can this type of emergence show up in quantum gravity? Well, the idea has been put forward of geometrogenesis, and please mind the word. It's just a fancy word for saying that there is something like a phase transition from which space and time emerge in a quantum gravity system defined in terms of non-spatial temporal concepts and structures. In particular, the analogy with the previous example is made a little bit stronger, as I will show you in the next example. You can interpret the group field theory, the field theory for spin networks, as the analog of the quantum field theory for the atoms in the condensed matter system, and treat it in the same way. That is, you would expect that from this point of view, that continuum space-time should emerge from the collective behavior of large numbers of the group field theory building blocks, be them written down as spin networks or simplices or a combination. And possibly such geometric description may be available only in one phase of the system, just like superfluidity is a property of the same system but only in one phase of the continuum limit. You can put forward the most precise hypothesis that continuum spacetime is a peculiar quantum fluid of this type of system. More precisely, that continuum spacetime is exactly a condensate of spin networks described by such a group field theory. Second, the other specific hypothesis is that where you should look for general relativistic dynamics is exactly the hydrodynamics of the system, of the quantum gravity system. If that is true, in particular, if spacetime is a condensate, so it's a peculiar quantum fluid, it is maybe the case that space-time itself is possible because of the quantum properties of the microscopic system, not in spite of those. The even more specific suggestion is that this condensation is not just a mathematical artifact, which would be already quite interesting, but is what took place at the Big Bang. So that the sense in which we say that space and time emerge at the Big Bang is actually quite literal. There is a pre-space-time, non-spatial temporal system that undergoes a phase transition at the Big Bang, after which a description of the same system in terms of space and time and geometry is available. Okay, and I skip the rest. Pictures for illustrating the concept. And now I give you a concrete example. A simple case, limited, recent, and only partially understood, in which exactly what I suggested seems to happen, and that realizes the notion of the same notion of emergence that we're seeing in both condensates in a technical way, which is actually the direct counterpart, the direct analog at the mathematical level. So what I'm going to show is a way in which you can extract cosmology, in particular quantum cosmology, from group field theory, that is from second quantized loop quantum gravity. So there are two main problems corresponding to the two main quantum gravity problems that I mentioned at the very beginning. One is to identify quantum states of the degrees of freedom in the fundamental theory, that admit a continuum space-time interpretation. If you don't have that, then you don't know what to look for, really, at the dynamical level. The second problem is once you have identified suitable candidate states, to extract an effective macroscopic dynamics for those states and check that it has to do with GR or cosmology or macroscopic spacetimes. Of course, I'm not going to tell you the whole history, the whole set of techniques that have been used directly or indirectly in this work. I only tell you the basic points. One basic point is that what you can show is that quantum group field theory condensates are, in a more or less precise sense, continuum homogeneous spaces of the type used in cosmology. That's also the first problem. You know what group field theory condensates are. They are a particular class of quantum states of the initial theory, and you can put them in correspondence in a controlled, reasonable way with continuum homogeneous spaces. Because they are condensates, just in the BC case that I discussed, they are described by a single collective wave function. And what it turns out is that because of the previous correspondence, this single collective wave function depends only on homogeneous, anisotropic, generically anisotropic geometric data. So the type of data you use in cosmology for describing space-time. In order to solve the second problem, once you have identified the group field theory condensates as the candidate states, you follow really straightforwardly the procedures of standard BCs. And what you can show is that the group field theory, that is in this context the quantum gravity analog of the Gross-Pritaevsky hydrodynamic equation in BC, is exactly a non-linear and non-local, by the way, in the sense that we specified, quantum cosmology equation for this collective wave function. So in quantum cosmology, you have a wave function as your basic variable. Usually it comes from quantizing mini-superspace GR. Here it comes as a collective variable from the underlying degrees of freedom, in the same way in which the Gross-Pritaevsky wave function comes out as a collective variable for the atoms of the condensate. Okay, this is just a note to the literature that similar equations have been obtained in different, related but different contexts by Boyewald and Dan, plus I forgot a bunch of 2 or 3 other people that I don't remember. Okay, so I have 5 minutes?
You have about 3 minutes.
3 minutes?
Yeah.
Excluding questions.
Oh, excluding questions. If we're leaving 10 minutes for questions, yeah.
No, it's okay.
So
I don't
probably wrap up pretty quickly.
Okay. Okay. If you keep in mind these 2 main messages, then I can discuss with you here and in private afterwards about the technical details. But a bunch of these technical details is what I want to discuss here briefly. So I told you that the basic building blocks of a simplicial geometry interpretation as geometric simplices, tetrahedra. So a generic state, and this tetrahedra depend on the algebraic variables that I mentioned earlier, say the algebra elements. A generic n-particle state in the theory will correspond to n geometric tetrahedra or n open spin network vertices. And that's a generic state for given assignment of the algebra elements of geometric data. We can be a bit more general. A generic state, even of this type, has no continuous space-time interpretation, just a bunch of disconnected tetrahedra. In this specific case in particular, because you're fixing this intrinsic geometric data, the extrinsic geometric data, curvature and so on, are totally unspecified. So it's even less of a space-time interpretation. So we define a reconstruction procedure. I cut it short. It involves an embedding, a little bit like in the causal set case, although the procedure is different. And I just tell you the result. You can define quantities out of this algebraic data that I conveniently label Gij, so that you're already well disposed to the interpretation. And what happens is that under appropriate conditions, and you have to specify the embedding procedure carefully, these are interpreted as continuum metric coefficients of a metric sampled at endpoints. Again, this is a little bit similar to what we do in causal sets, or you would do in any discrete theory, actually. So you have metric coefficients sampled at endpoints corresponding to the n building blocks of your state. But then you have a classical criterion for homogeneity, dictated by the way you define the embedding procedure, which is that, well, if all the data you reconstruct at the endpoints, then your state is compatible with an homogeneous geometry. Okay? That is, you can lift this at the quantum level. Not only you have the same geometric data, but more generally, if your quantum state is given by tetrahedra building blocks, all with the same wave function, that is all in the same quantum state, then you have a quantum notion of homogeneity. In the field theory context, you can use the second quantized language to consider superpositions of states of arbitrary n, and in particular, you can send n to infinity, that is, you can improve arbitrarily the accuracy of the sampling. You can consider an infinite number of points. But this type of states are the definition of a quantum condensate. A bunch of atoms, building blocks, all in the same quantum state. It's actually the simplest ansatz for a condensate. And I just showed in what sense, I just hinted to in what sense these are homogeneous spaces. Okay, you can construct different choices of such condensate states. Let me discuss only the simplest for brevity. So the simplest Gross-Pitesque approximation is the one I've shown. So you take the exponential of a creation operator convoluted with a function on the single particle data. And this is just a bunch of an infinite number of single particles, these spinetto vertices, all with the same wave function. And this is the simplest. There is another choice that's been, well, the building block of that is this dipole condensate that has been already introduced in the spinform literature. And you can also see it from the condensate point of view as a sort of Bogolyubov improvement in which you take into account two particle correlations, but nothing more. So for simplicity, I'll focus now on the first. So the main points to remember is that this state depends on a single collective wave function, like in the standard condensate, and is a wave function for homogeneous anisotropic geometries. But still, it's a truly non-perturbative quantum state. It involves an infinite number of degrees of freedom, just like in the BC. Okay, I'll skip that. Then second
We'll
part.
probably wrap up if we're going to have any questions.
Yes, I hope there are, and I need. Okay, here I'll be very fast, and then I put two slides, but they are really just for questions, for eliciting questions. Sorry, you should not have told me that I had 15 minutes earlier. I was so worried that only 2 minutes. Okay, so you make the story short. You take these answers just like in the standard BC, you plug it in the fundamental quantum dynamics, you extract an effective equation which has a linear part in terms of the effective of the collective wave function and a non-linear term. Because the collective wave function is a wave function on the space of homogeneous anisotropic geometries, this is like a non-linear extension of quantum cosmology. But it is the analog of the Gross-Pitesque hydrodynamics. Okay, so then you can show that in particular models the effective dynamics gives the Friedmann equation, but again, they are very particular models. I don't have any general result to show. Okay, I'll skip this part and I will only make two comments. So, okay, first of all, this is really the first derivation that I'm aware of quantum cosmology at the dynamical level, coming from a fundamental quantum gravity formalism. But more appropriate to this context is the first concrete example that I know of an emergent spacetime directly from a fundamental quantum gravity formalism. It's a simplified case. I'm only extracting homogeneous geometry, so it's almost trivial. But still, it's interesting for the following foundational issues. So the issues here are very brief and have to do with the way cosmology emerges. It emerges as the hydrodynamics of the fundamental quantum gravity model, not as a quantum theory per se. And in fact, it comes with a non-linear equation. So you're outside the standard formulation of quantum mechanics. So maybe it calls for a new interpretation of quantum cosmology. Maybe it's not quantum at all. It should not be quantum at all. Maybe there's no such sense in which you have a probability for the whole universe, although you can still compute expectation values, but in the hydrodynamical sense. You have a distribution over the configuration space. And I think that it could be interestingly related, but it has something to be discussed with non-linear extensions of cosmology discussed by several authors, including Daniele, who is here. And let me just put forward the concluding comments really for the discussion, because they are more on the philosophical side of the story, where I have more to learn than to say. So I think that this example shows that the same main definitions of what emergent means I should emerge, how you should see emergence of space-time in quantum gravity are indeed realized. In this, again, it's a simple example, but the main features, you can see them: the role of limits, the role of approximations, the novelty of the properties, the crucial role of the quantum properties of the underlying system. And I would say that empirical coherence, according to what I said earlier, is not in danger, assuming that the system can be developed further and you can extract effective properties at the cosmological level from the microscopic description. Those properties may be testable even though you cannot see the fundamental atoms of space, in the same sense in which you can do the same for atomic theories. And last, let me just take the opportunity to mention the word ontology, which usually you're not allowed to do in physics conferences. And I just put forward questions related to ontology. So is space and time real? Are space and time real if they are emergent according to this scheme? So maybe we're actually going from the necessity of spatial-temporal ontology to the opposite. Maybe there's no ontological relevance for space and time at all. And I told you that maybe space and time emerge only one phase and only at a certain level. But then what is the ontological status of non-spatial temporal regimes? For example, the non-geometric phases of the same system. Last, maybe you have to call for a multi-level, non-reductionist ontology. And here I stop.
Using your BEC analog, at the emergent level, you have a quantum theory governing this dynamics, and also at the particle level.
So you're talking about the realistic, real-world BEC or the quantum gravity exactly?
No, the real BEC. Now, what confuses me about the quantum gravity then is we know the dynamics of space-time, but then at your simplices, right? What governs their dynamics? I mean, I was worried that there's some kind of begging the question going on where you identify some history of simplices with something that's going on in the dynamics of space. So what governs...
Okay. I think I understand the question. So, in the quantum gravity case, the fundamental definition of the dynamics is given by the group field theory model of your preference. So, which is a field theory and is a quantum field theory. Usually it's taken to be worked out in the formalism of standard quantum field theory, modulo the fact that it is a non-local field theory in the combinatorial sense I mentioned. So the naive answer is, you have a quantum formalism for the building blocks as well. But I don't want to neglect the fact, to gloss over the fact that it may call for a reinterpretation even of the quantum formalism, because it's not obvious what the notion of unitarity is for this particular field theories. You drop the notion of locality, as I said, so many other notions of many other ingredients of the standard interpretation of quantum field theory also may need to give way. So technically, up to now, it's been treated as a standard quantum field theory, but at the interpretation level, there will be lots of work to do to see how much you can really use the same interpretation as in standard quantum field theory. But you have formally a quantum field theory for the building blocks.
All right, we're absolutely out of time. Tom, get up here.